All right, so here we're going to cover fields and attractor logics, which we'll talk about in lecture and in class, but this video is going to cover the grasshopper part of it. And of course, probably the archetype here is this form style hexagon-based tractor facade that we kind of see in this photo here, right? And it's going to lean heavily on the Lunchbox kind of suite of plugins. So, just as a kind of start and as a beginning, I'm gonna use a simple, right, kind of like rectangular surface, more sort of long-ish, like that. Just kind of eyeballing that for now, right? And to link it in, right, use a kind of surface component, right click, set one to get it in here. All right. So all these will, most of these, right, will live under the Lunchbox kind of plugin here under panels, right? And the sort of very obvious one is the hexagon cells right there. So the surface goes into surface, obviously, right? And then you can kind of see, of course, right, because of the surface I made, the kind of proportions, right, are sort of off. So let's do sliders, integer sliders. Actually, 10 may not be enough. Let's do 0 to 20. Copy them, right? This goes into the U and, oops, and the V, right? And then we'll kind of experiment with this to kind of find, of course, the U divisions are that way. So probably, right, something like that, right? And obviously, this is something that you can kind of change or modify, right, based on what kind of visual uh, you're really kind of looking for. And we actually might come back and change this into something denser later. Again, the T parameter, as we've kind of learned before, actually is really changing the angle. So this actually just uses your sort of typical number slider, 0 to 1, and you can kind of change, right, this, right, the angle. The default is set to 0.25. Oops. 0.25, which I'm going to keep there for now, right? Okay, so from there, right, understanding that we're going to be using a scaling, right, operation, so scale, okay, which looks for a base geometry scale. In this case, our cells, right? These are cell outlines. These are closed polyline outlines that we're going to scale, right? So this goes into kind of there. By default, you'll see what happens is it scales the entire thing, right? Because we haven't actually given it independent scaling centers to scale off of. Now, obviously, because these are actually, there's 53 of them, right? And they correspond to 53 centers. So when we give this to the scaling component, it actually is smart enough to know that, oh, right, that center correlates to that cell, right? And because again, data matching, generally Grasshopper will kind of do its best guess for this kind of stuff. Okay. Now the idea of the attractor is sort of obviously based on let's say if I had a certain point, right, then it's kind of measuring different distances in between them, right? And then based on that distance, we're telling it to do something, right? Whether it's scale up, scale down, thicken, offset, extrude, et cetera, right? So this value is basically kind of this distance value is basically kind of what's driving the sort of the entire thing, right? So because of that, right? So obviously this kind of goes into kind of how you can build the logic. Let me clear those drawings. But we're going to do a distance measure, right, by default, right? And we're actually also going to create a point. So just to make it a little clearer, I'm going to create a point out there for now and use a simple, right, again, point container. That one point, click on the point, link it in, right? This is point B. All of our centers, right, these are the center points of the cells, go from point A, right? So I should be getting, in this case, 53 different values, right? And they can be drawn out if you want to, right? I'm going to draw a line uh, just so you can see them. The same thing, right? Line 2 points, right? These are all the lines, right, that are kind of being measured as distances. Okay, so these distances, what we're going to do, similar to what we did with the image mapping, right? We're going to use the remap component. We're going to use the bounds component to sort of be able to remap them and set them so their scale doesn't go wonky, right? Now, I can actually use this right away. So if I do, and you'll see, essentially like this is what happens, right? And what's happening is because these numbers, right, these are distance numbers, right? This is 150, 160, whatever, right? These numbers are actually being used as straight up scaling factors. So these cells are being scaled to 58 and 110 and whatever, right? So they're much larger, right? So that's kind of why we actually need these remap and boundary functions, right? So distance, if we look at its bounds, then we'll get basically the numeric domain. So what is the smallest and what is the largest, right? 53 to 184, right? That's kind of like the range of measurements we're getting out of there. And obviously this will change, right? Because I can move my attractor point around, right? And it will change. And that's what makes this particular pattern or workflow very useful because it's adaptive, right? The distance values goes into the values that we're going to remap, right? Our source comes from the bounds, and our target, just like the one we did before, let's say, right, we're trying to remap it so it's a scaling factor. We're trying to keep it within this facade. So it's going to be one, right, at the large. You're not trying to make it bigger. You're right. You're always kind of trying to scale it down, right? So the largest scaling factor is one. So again, we'll construct domain, normal construct domain, right? And on one end, let's say this one we want to adjust a little bit. So let's do a 0 smaller than 1.00, make it 1, right? The other one I don't, which would be the minimum. So I don't anticipate changing it much. I'll just do a 0.1 straight up from the panel, double slash 0.1. Okay, and this is our target. Now this then replaces all our scaling factors, and now we have something working. Okay, we can kind of hide if you want to, Control Q, right? Hide some of that stuff. And with the scaled portion, then we can kind of see if I do move, right, my attractor point around. Now, right now, what the attractor is doing is that it's saying wherever your point is, that's your largest modules, right? If you wanted to flip it again with the remap, then basically these two, right, can be inverted, right? So if I wanted to, let's say do that, right? So I'll replace that. I'll replace this, right? And now the attractor works in the inverse, right? So whatever it's most closest to, right, gets scaled the most. Okay. Again, observe the behavior, right? So I can kind of control on this end what the, right, let's say the largest kind of scaling closest to one might be, but you can kind of like make it a little smaller, like 0.9. If you actually also, I did make that value a kind of static value, but if I did want to actually also be able to adjust the other end, then I can kind of do the same with a slider as well. So I can kind of adjust the minimum here. Okay. So that's the same. Doesn't kind of really change much over there, right? All right, that's a simple attractor, right? Single point, right? Moving it around, simple scaling operation. Obviously, this doesn't feel maybe it doesn't feel dense enough. So I'm actually gonna like, let's say double my divisions here. So 40, and actually this one, let's make this 8, something like that, right? So with this, then you get a little bit more clearer, right? Kind of you need some room, right, for this effect to kind of take place. and kind of be visible, right? So you'll be able to kind of position things and move them around a little bit more. Okay. All right. Now, variation two that you kind of see on our Canvas page here, which is like right here, right? It's very simple. So we'll actually just kind of what I'm going to do is just kind of hide things, and some things I actually just might like copy down. But let's go into and let's find the major things first, right? So this is kind of like, let's say, building the attractor logic step by step within Grasshopper, obviously kind of using Lunchbox as sort of a hexagon kind of cells. But Lunchbox also has actually built in about two of these, right? Attractor and attractor wave, right? Built-in components that just like do attractors by default, right? So let's start with the first one, okay? And I'm going to hide kind of what we had before, right? Just reverting it back to kind of basically this, right? And I'll actually copy our surface and point inputs down, okay? And for this example, I'm going to use the try B from Lunchbox under panels, triangle B as an input. And actually, I'm going to copy these UV sliders as well, just to redo them. All right, surface goes to surface, U and V. Again, look at the proportions, should be okay. If this red overlay is getting really dark, it's because, you know, the stuff above is also just turn it off, turn off the display. And let's go from there. Okay, so we have panels, right? Try B panels, kind of change these to get, you know, proportions of your liking, right? Same thing as before. And from there, I'm going to go into looking at this, right? So attractors, these are points, right, of one or more. So it actually will do multiple if you eventually do give it multiple, but let's just stick with one for now. Because the thing with multiple attractor points is that things actually average out, right? You can kind of wash out the attractor effect, right? And then the targets and then a domain, right? So domain actually is the same thing from above. We're gonna just copy what we had from here, move it down, domain, right? And then we'll also use the typical scale component here, right? So the geometry that we're going to be scaling are the panels, right? So the panels go straight into geometry over here. And again, it's doing this, that's fine. Our centers of scaling. Now this, right, only gives us panels because this particular component gives us surfaces, right? Different from above. The one above the hex actually gives us cells and centers. So these are polyline curves, they're not panels, right? That's because hexagons, if applied to curved surfaces, they're not planar, right? Triangles always will be planar. Um, Centers, right? So what we have to do with this actually is just to do a very simple area calc, right? We pull out an area calc, and then from the area, right, we can grab our centers, right? So these centers go into there, and now the scaling is now, right, working correctly. And as you can see, as I hide these, Control Q, I'll hide the surface as well, right? These are now scaled down surfaces, right? They are actual surfaces with a scaling factor, static scaling factor of 0.5, right? So now we have to figure out this, right? So our attractors come from the point that we have linked above, right? So this point goes into attractors. Our targets come from our area centroids, right? That's kind of like where it should be measuring off of, right? And then just to kind of look at this, right? So it actually gives you a lot of information, both like values, the new scaling values that you're getting, which basically kind of replaces some of this stuff that we're doing in here, right? Above. It'll give me vectors as well, which can be useful later on, maybe for, let's say, extruding, right? Using a vector. and also the distances, right? So they're all kind of combined in one component, basically, which is kind of nice. All right, so values good in here. And now I will also hide the area so it doesn't kind of get in the way. So now you'll see using Lunchbox's attractor component, we have something similar, right? With just a couple more options, right? And so in this case, I'm going to actually duplicate another point, right? And actually set duplicates, so set multiple points and select both of those at once. And what you'll see is that it will actually start to kind of try to use both of these points as attractors, right? So if I actually kind of scale down my domain a little bit, right? You can kind of see, right, how it can take both inputs and have them work at the same time. Now, again, it is sort of an averaging out, right? And so you can kind of wash out that effect very quickly, right? So I usually don't do point attractors with multiple for the most part. Usually kind of use them with singles because the effect is a little bit just more prominent, right? And the range is a little bit more prominent. Okay. So obviously this kind of controls the sort of field of influence, right? Kind of how far you want it to propagate, all this sort of stuff. And that works pretty well. Okay. So very quick. And I am again going to just actually after we copy it down, but basically kind of disable all these. All right. So I'm going back to Lunchbox, right? Under generate again, find attractor wave, right? So this is one. This one's fun. We'll need to actually modify some things, but it's kind of essentially the whole thing from above. So we're just going to copy paste it down here. And what we're going to do is basically kind of swap out values for this guy here. Okay. So if I just delete the original attractor component, right, and it only has kind of like one extra sort of thing, right? So attractors still the same, right? And actually, sorry, my cat's kind of coming in the way. Targets still coming from the area centroids, right? Domain doesn't change. And then the values go to scaling factors, okay? And obviously, the one thing you want to do is also just like reactivate the preview for this, right? So turn that on. And then you'll see something a little bit different happening, but still fun, right? And then I'll have a slider goes from 0 to 1.000. That is the frequency. So over there, right? Okay. Now, the one thing to modify here is, let's see if this is dense enough. Basically, I'm going to want my divisions to be a lot higher. So 40, 20, right, might kind of sort of work. And let me make the gradient a little stronger. So you'll see essentially like as a sort of like very low number frequency, this operates kind of basically like a typical attractor will. But what it does is actually it's kind of basically doing almost like a three-dimensional ripple, right, or a sine wave curve. And that's what the frequency is coming from a sine wave kind of frequency. And as I up my frequency, you'll see the let's say mountains and valleys, right, coming in. So it's almost like a ripple, right, animation, right? So that's kind of fun. Obviously, this still, there's a kind of need to sort of kind of find a balance, right, between kind of visibility, right, what your smallest, larger kind of modules are, but basically this. And you can kind of up these divisions to something much higher because let's say let's do up to 100, right, for both U and V divisions. right? So you'll get basically kind of a lot more density. But of course, with more density, it's a little bit harder to drive, right? So there's a little bit more kind of nuance there, right? But you'll see essentially that's the effect, right? So I tend to like this when it's kind of like a larger gradient in between things, right? And you'll get kind of more, a little bit more kind of visual blending in between them. But you know, but essentially this is what it does. And I forgot actually what it does with multiple, so we can try multiple points. Oops, that multiple, let's see. Okay, yeah. So when you do multiple, what's kind of cool is that because the waves cancel each other out, right? So you actually start to get an interference pattern. Very, very similar, at least visually. I'm not saying it's so scientific, but like sort of like the wave tank experiments that you might have done in physics, high school physics, right, with a wave tank, right, and the two slot wave experiments, right? So you can kind of see how these sort of two point epicenters, right, with let's say if they were wave generators, point wave generators, how those waves would actually, those ripples would actually interfere and cancel each other out, right? So same kind of ideas behind, let's say sound wave, active noise canceling, right? All this sort of stuff. Pretty cool. Okay, so that's the third variation. I'm going to hide all those again, right? And then we're going to jump to the one that's probably in many ways the most controllable. These are the points. I'm going to kind of move them out of the way. A bit more controllable, but probably kind of like similar to the example, right, that we're kind of seeing here with form style. And I'm actually going to draw a curve. So, oops. So I'm gonna draw some right curve that looks like that. Okay. And this is going to be the attractor curve example, but again, it's just an adaptation. So we're actually going to take the first one, the one on top, Control C, Control V, move it down, right? And this is sort of like a 4-in-1. And we're going to change things out a little bit, right? So instead of a point, right, we are actually going to do a curve container. Step one, I'm going to link in the curve I just drew, okay? And this is actually using a component called curve closest point, curve CP. I usually just type curve CP, right? And what it does is basically you can project a lot of points onto a curve. Basically, we're going to project all of these cell centers, right, which are all of these, and project them onto the curve. So our curve goes in here, right? And actually, again, this is, typical blob, sometimes just to say, oh, those are inputs, right? Um, and I'm going to actually move everything that way a little bit, just so the sequencing is a bit more clear, right? And these centers go into here, right? And as soon as you do that, you'll see, oh, there's a whole lot of lines on here, right? And just to kind of like make it very obvious what it's doing, I'm going to annotate and draw. So basically, essentially, each of these points is being drawn to a parallel, perpendicular point right on the line. So it's saying, okay, what's the closest, right? Where are those perpendicular points? And then, oh, it's probably here, sorry, right there. And what it's doing is that's the closest distance from this point on that curve, right? So it's finding all of them, right, at the same time. That's what curve CP is doing, okay? So it's very useful for this particular measurement because then we can measure those distances, right? So like before, right, instead of saying measuring all to like one or two of these attractor points, now we're measuring it based on that curve. And so these points then become the inputs for our distance measure, right? And I believe everything else actually stays the same. I'm going to hide this. I'm gonna hide that. You turn that on, right? So same thing. And as you can kind of see, everything kind of actually operates similarly as before. You can kind of invert it if you want. So same thing, like invert it that way, move this down this way, right? So it's more larger where the curve is. But the form cell example, um, right, is sort of like denser where, let's say, the curve is, right? So it would be kind of more like this, right? This sort of version. And so, right, if you have the right density in terms of your hexagon cells, then obviously I can edit my curve points, right? And it would update, right, based on that density as well. So makes it very adaptable, right, to kind of play with, right? And it's not based on a single point, it's based on a curve. And that's it. That's the attractor curve kind of version of this. And obviously, right, you can, again, with most of these attractor things, because we're working with some kind of distance value, right, that's kind of been measured out, this is all something you can adapt, right, into a scaling factor, a rotation, extrusion, all sorts of things. All right. All right. That's it for the attractor fields.